So the CCMA series is sponsored by the Department of Civil and Environmental Engineering and the CCMA Fund, and was established in honor of Professor Cheng Mei in CEE for his distinguished seminal contribution to a range of problems in fluid dynamics and mechanics. And our speaker today is going to be focused on a topic in geology and chemistry, and I'm going to leave the introduction to my colleague Ben Kokar to do. Thank you for coming.
So I'll just say a couple words about Professor Dr. Kretzschmar. So received his PhD at North Carolina State. That was in 1990. After that, moved on to ETH ultimately in Zurich. So he's a world leader in environmental biogeochemistry of understanding cycling of toxic metals and metalloids. Also, I noticed he had a couple recent publications on antibiotics as well. Yeah, so no, really? Tetracycline? I thought there was tetracycline. Okay, well, never mind. I was wrong.
I know one scientist out of my group.
Okay, good. All right. All right. So I'll leave it at that. So today he's going to talk about arsenic and its cycling in peatland environment.
Well, first of all, I would like to thank Lydia Ruben and Ben Kokar for inviting me. It's a great pleasure and also an honor to be able to speak in the seminar series. I would also like to thank Carol who helped setting up the program. It was very exciting and very enjoyable. And I enjoyed the beautiful campus already. It's a pity that I'm here only for a day. So in my talk today, I will present some work that mainly two PhD students did, Peggy Langer, who graduated a while ago, and Laurel Thomas Arrigo, who just defended her thesis. And I also want to mention Christian Mikuta, who was a postdoc in my group for many years. He's now starting a professorship at the University of Hannover in Germany. And I also would like to acknowledge some collaborators, James Byrne and Andreas Kappler from the University of Tübingen, who helped us with Mörsbauer spectroscopy, and Peter Planer-Friedrich and her student Regina Lohmeier from the University of Bayreuth in Germany, who helped us with sulfur speciation. So today I will talk about this beautiful small wetland in southern Switzerland in the Swiss Alps. And the reason why we got in, it's a little loud. The reason why we got interested in this is that this wetland was found to be naturally enriched in arsenic. And we're interested in studying the site to understand better how arsenic behaves in such organic-rich environments. It interacts with some other major elements, mainly carbon, iron, and sulfur. And the reason for why this is important is that such wetlands could change in the future with climate change. The hydrology in the Alps will change quite a bit, so some of these wetlands might fall dry, and we're interested in seeing whether they could be potential sources for arsenic export. Before I go into this particular system, I'd like to give you a little bit of background on arsenic in general. So as you probably know, arsenic is a naturally occurring trace element which occurs in all rocks, sediments, and soils. But it is also an important environmental contaminant, for example, released by mining activities, by agriculture, or industrial activities. And the problem with arsenic is that it's fairly cancerogenic. It's not the acute toxicity, it's the cancerogenic activity that occurs if you take it up over long time periods. And because of that, the World Health Organization recommends a drinking water limit of 10 micrograms per liter, which is a very low concentration and sometimes not easy to meet, even in uncontaminated aquifers. And the reason for this is very often related to redox processes. Very general, one can say that if you have oxic soils or groundwater aquifers, they typically contain some polycrystalline oxides of iron-3, which are very good sorbents for arsenic 5, which is the dominant species of arsenic under oxic conditions. And so the result is that arsenic mobility in oxic aquifers and soils is fairly low. However, if the soils or groundwater aquifers get reduced, you can have iron-reducing conditions. So these sorbents can dissolve and the arsenic can be reduced to arsenic-3, and that greatly increases the arsenic mobility. Now, there's a lot of arsenic research in the literature, of course, and I think there are two big problems that drove this research over the past decades. One is mining. So arsenic has several different applications, as I mentioned already, and the world mine production of arsenic in 2010 was about 45,500 tons. And in many cases, it is not even the arsenic mining itself, but it's that arsenic is associated with many other sulfide ores mainly. So other metals are mined, and in the mine tailings, you find a lot of arsenic, often in association with pyrite and Arsenian pyrites. So you can have acid mine drainage developing, and that can lead to mobilization of arsenic. And there's a lot of research on arsenic associated with mine tailings. So mine tailings, I think, are a problem, but they're fairly easy to control in terms of exposure because usually they're not in the highly populated areas. You can also fence them off. You could cover them with something. You could minimize human exposure to that arsenic. But the second problem related to arsenic is the groundwater contamination. And the most famous case is probably Bangladesh. And this was basically, just very briefly, the history was that in Bangladesh since the 1970s, there was a massive increase in the use of shallow tube wells for drinking water. This was mainly to combat waterborne diseases, which is of course good. But in the 1990s, it was discovered that a lot of these tube wells had too high arsenic concentrations, exceeding the World Health Organization drinking water limit. And so this affects not a few people, but tens of millions of people who are exposed to high drinking water arsenic. In addition to that, since the 1980s, there's also an increase in rice production during the dry season, meaning that you use groundwater from shallow tube wells to irrigate rice fields. And this is an additional exposure pathway if arsenic is taken up by rice. So there was a lot of research in Southeast Asia and in other countries understanding arsenic. Meanwhile, there are many other aquifers in the world known to be high in arsenic, some in Southeast Asia, also some in Europe, some in the US. And in many cases, these are mineral-dominated aquifers, and it's related to redox conditions in many cases. However, what about these wetlands? I'm now coming back to the peatlands. There's a lot less known about arsenic biogeochemistry in organically dominated systems. We have very little mineral material and a lot of organic material. So what we have to expect is that we have a strong redox gradient in such systems because we have some surface waters here. We have photosynthetic algae growing there. We have plants doing photosynthesis, producing oxygen during the day at least. So we can expect oxic conditions up here. We might have a zone where we have variable redox conditions, and then we get into a zone of the peat which is permanently water saturated and anoxic. In these surface water, we typically find these so-called flocks. Flocks are complex associations between microorganisms, algae, and mineral particles, in this case mostly iron oxides. And these were also found to be, in this case, very rich in arsenic. So the question here is, what is the speciation of arsenic, iron, and sulfur in such a system? And how dynamic is it, and how does it react to changes in the system? So before we started this, we looked through the literature to find out what is known about arsenic binding to organic matter, to natural organic matter, and there was not much. I mean, there were some proposals. For example, this is proposed very often that arsenate could be bound through a metal bridge to organic, in this case, carboxyl groups that complex the iron, and that is linked to an arsenate molecule. But it was also proposed that there could be direct covalent bonds between arsenate and some organic functional groups. But this was never spectroscopically shown in natural systems. Another idea that we had basically from plant physiology, because in plant physiology it is known that arsenic is often
present as arsenic-3 inside the plant, complexed by thiol ligands. And so we thought maybe this is also an important species in peatlands where arsenic is coordinated to sulfur. So the objectives of the project that I will show today is in the first part, I will show you some work where we studied the speciation of these elements in the peat core itself, in the deeper peat layers. And the question we then raised is what happens if such peat is exposed to atmospheric oxygen and gets oxidized? Does that increase the arsenic mobility? And in the second part, I will focus on these floc materials from the surface water. And also we wanted to look at the speciation and then understand how does that change if such flocs are exposed to reduced species like iron-2 or sulfide. So this little peatland is like I said, a minerotrophic peatland, meaning that it receives water from the surrounding. It's about 2.7 hectares large at about 970 meters above sea level. It has a mixed bedrock mineralogy, mainly some metamorphic rocks. And it was discovered in 2006 in this paper that there is an inflow coming in which has a much higher arsenic concentration than the outflow. And also it was shown that the peat itself was enriched in arsenic, also in some other trace elements like selenium and uranium. So the first thing we did is we went in there and we took some peat cores, and on site we characterized the peats for pH, EH, electrical conductivity, water content. We took samples for elemental analysis, and for synchrotron spectroscopy for speciation, we shock froze the samples in liquid nitrogen, transported them to the lab, and then everything was done in a glove box so to prevent oxidation. So just to give a little summary of the basic geochemical parameters, the redox potentials we found range from strongly anoxic to oxic, pH values of the peat samples in the moderately to weakly acidic range, arsenic concentrations from very low to up to 1,800 milligrams per kilogram, that's per kilogram dry mass of the peat, iron between 3,000 and 60,000 milligrams per kilogram, sulfur between 30 and 40,000, so quite variable composition. And the organic matter content was up to 100%, so up to pure organic material. But we also hit the base rock in some cases where it had a lot of mineral material. This is just a general summary. So first I would like to show you two results of two different peat cores. These are like examples. We sampled more cores, but what I want to show here is that the arsenic depth distribution was not homogeneous. We had some cores which were actually, so in pink you will see the arsenic, and gray this is carbon, the orange is iron, and the yellow is sulfur. But I just want to focus on the arsenic here at in this slide. So you can see that in some cores we had arsenic accumulation mainly in the top 40 centimeters, but in other cores we had the greatest arsenic accumulation in deeper peat layers. I think this has to do with the way the water flows through this peat, and it is probably a result of the whole formation of the peatland. The water flow can change over time, and it's very heterogeneous. So what we had to do there is to study the speciation. We picked different horizons or layers of peat that were enriched in arsenic, some surface layers and some deeper peat layers, and then we did synchrotron spectroscopy on those. So I will now show you some arsenic EXAFS spectra. And if you're not familiar with this spectroscopy, it doesn't matter, because you can take these spectra as fingerprints for a certain way of coordination and redox state of the arsenic. And the nice thing about this spectroscopy is that it's additive. So if we're able to measure a library for known compounds with known coordination chemistry in redox state, we can use these spectra to explain an unknown spectrum by a linear combination, because it's an additive behavior. And so here I show you 5 references out of a big library that turned out to be relevant in this case. The top spectrum is realgar. This is an arsenic sulfide mineral. Then we have arsenic 3 and arsenic 5, so inorganic arsenic species sorbed to ferrihydride. This is a proxy for arsenite and arsenate adsorbed to iron oxyhydroxides. It could also be goethite or something else. And then we have 2 references called arsenic 3 NOM. And these are 2 compounds that are arsenic 3 complex to organic thiol ligands. And you can see that these 2 spectra are fairly similar because they have the same coordination. But you can see the other ones are clearly different, and so you can view them as fingerprints for these different compounds. Now, if we look at the peat spectra, 2 from surface layers and 2 from deep peat layers, you can firstly see that the surface layers have a clearly different spectrum than the deep peat layers. You have more oscillations, meaning it's a more complicated spectrum. Here you just have like 1 frequency, meaning it's just basically 1 contribution. And if we do the linear combination fitting analysis using these references, we find that the surface peat layers contain a lot of realgar. They contain also some arsenic 5 and arsenic 3 adsorbed to iron oxides. And they also contain some arsenic 3 bound to organic sulfur groups. However, interestingly, the lower peat layers contain only arsenic 3 complex to organic thiol groups. And this was a very surprising finding, actually. We had expected a lot more arsenic minerals like arsenic sulfides in the deep peat layers. And this was also looked at by, these are some EXAFS shell fitting results. Here you can see the structure of these 2 reference compounds. So you see the arsenic coordinated with 3 sulfur groups, and they're then bound to organic rest. And it's exactly the same here. The 2 green ones, these rests are basically the same molecule here, and you have actually the same configuration. And on the right side, you see shell fitting of the first shell, the real part and the so-called Fourier transform magnitude part of the EXAF spectrum for the 2 references on top and the one of the peat samples in the bottom. And you can see they're really identical. And the fitting results from the shell fitting also agree very well, telling us that arsenic 3 in the NOM was coordinated with 3 sulfur groups at an arsenic sulfur distance of 2.26 angstroms, which is identical to these references. So this is really, I think, a very clear proof that it's this species. We also did some follow-up studies using a technique called micro XRF and micro XAS. What we do here is we prepare a thin section of the peat, which is in that case embedded in a resin. We also try to do this under exclusion of oxygen as far as possible. And we take it to a synchrotron beamline where we can focus the X-ray beam to a few micrometer spot size and then scan the sample to get elemental maps. This is what you see here. And on the left side, you see the surface layer, and on the right side, an example for a deep peat layer. And if we look at these elemental maps for a moment, you can see that in red, we see arsenic, in green iron, and in blue sulfur. So you can see in the surface layer, we have a lot of these red little hotspots, which are realgar crystals, particles. So minerals tend to form these nice hotspots. In the deep peat layer, we find a completely different local distribution of arsenic. So the arsenic is associated with these organic fiber structures, and it's not associated with iron. And you can see that it's correlated with sulfur because this gives this purple color because these are also sulfur-rich structures. And so we can see here that the arsenic is really bound to these organic structures and not present as mineral phases. It's basically just supporting the previous result. And you can then go in and you can collect, go to certain points in the image and then collect EXAF spectra and verify the speciation. We also found another species in the deep peat layer using this technique, and that is some very small amounts of arsenopyrite on a few spots in the sample. So this is just an example that this type of technique can also be useful to identify some really minor species that you overlook with other techniques. In using bulk EXAFs, you have no chance to detect, let's say, 1% or a few percent of a species. But with this technique, you might discover it. But it's still, I mean, the result is still very consistent. So now we know the speciation of sulfur in these peats, and we were now interested in knowing what happens if this peat is exposed to oxygen. How fast will it oxidize, and will this lead to mobilization? So we did an experiment where we took field moist peat samples from the deep layer, actually from both layers, but I will only show the results for the deep peat layer. And we fill them in these incubation bottles that are sealed through a sterile filter that allows gas exchange, but it doesn't allow any microbes to go in or out. So if you sterilize it inside, it remains sterile unless you have something regrowing in there. And then these bottles were, so part of them were sterilized with gamma radiation, and part were left with the natural microbial community. And then they were incubated for up to 180 days. And we followed the speciation changes over time and also the solubility of arsenic by doing water extracts and then measuring the dissolved arsenic. So let's see what happened. First, I want to show you that the sterilized treatment, in fact, did remain sterile over the entire time period. I mean, this is not always the case, but I think we were lucky with this. So you can see here ATP activity, and you can see the sterilized treatment had no ATP activity over the entire period, while the non-sterilized treatment had some biological activity. In fact, in the surface layer, it's not shown here, it was much higher, the biological activity. We didn't do any microbial community analysis. I think this would have been interesting, but we only monitored ATP activity. In both cases, pH decreased, pH increased, as you would expect it. So let's first look at the arsenic speciation. And here you see these are EXAF spectra, and from this, in the middle, let's focus on this. These are the linear coordination fitting results of these EXAF spectra for 0, so the initial, and then after 90 days and after 80 days, in orange, the non-sterilized, and in blue, the sterilized treatment. And you can see that in both cases, we had some oxidation of arsenic from arsenic 3 to arsenic 5, but it was not complete. We had overall, over 180 days, maybe up to 30 or maybe maximum 35% oxidation. And the rest was still arsenic 3 bound to the organic matter. And the soluble arsenic by the water extract clearly increased in both cases, and all the water-soluble arsenic was arsenic 5. There was no water-soluble arsenic 3, and this makes a lot of sense because arsenic 5 does not bind to thiol groups. Only the arsenic 3 is complex to thiol groups. So it gets oxidized and then it gets released from the peat. We look at iron and sulfur speciation. We found that, so iron, again, this is day 0 and day 180, non-sterile and sterile. And we found that in both cases, we had initially some pyrite here, the dashed bar. And we found that after 180 days, in both cases, the pyrite was completely oxidized. And the iron formed iron 3 oxyhydroxides. I mean, that's not surprising, but I mean, it was still interesting to see that there was very little difference between the biotic and the abiotic treatments. It was actually surprising. For sulfur, we also observed a little bit of oxidation. So there was mainly reduced sulfur in these samples, and this is derived from sulfur-xanes spectra. This is a typical sulfur-xanes spectrum in which you see here at the lower energy, mainly the reduced sulfur, and at the higher energy, the oxidized sulfur groups. And you can then follow how much reduced and oxidized sulfur there is, and you see a little bit of oxidation of sulfur. You also saw some sulfate forming that went into solution, but it was not completely oxidized. So the conclusions of this part are that the natural organic matter is indeed a very dominant sorbent for arsenic-3, especially in the deep peat layers. And in this, arsenic-3 is coordinated with 2 or 3 sulfur groups with this arsenic-sulfur bond distance of 2.6 angstroms, which is consistent with our references. Also, some minor amounts of arsenopyrite were detected in the deep peat layers, and the surface near peat layers, which I didn't talk so much about, but they contained mainly realgar and also some arsenic-3 and arsenic-5 sorbed through iron oxides, and also a little bit of this NOM type binding to sulfur. And the experiment showed that exposure of these deep peat layers, that they actually result in a mobilization of arsenic. So it's actually a very different behavior than you would expect from a mineral aquifer, where oxidation would result in a immobilization of arsenic, and a reduction would result in a mobilization. So in the next part, I will show you some more recent results where we looked at these flock materials that were collected in these surface waters. So we went back to the field and we collected these iron-rich flock materials, basically just by scooping them out of little streams. We washed them and sieved them, and then freeze-dried them for characterization and used them for experiments. And of course, we had to characterize them as well and look at the speciation of arsenic, iron, and sulfur in these flocks. And the first slide I'm showing is some ATR, FTIR, so infrared absorption spectra of the flocks. And the most prominent feature here was this very strong absorption band around 1052 per centimeter wave number, which is indicative. It's a CO stretching band, which is indicative of acid carbohydrates, and it's very typical for EPS-like organic matter that is, for example, excreted by algae or microorganisms. But there's also some humified organic matter in these flocks. The elemental composition showed that there was a lot of carbon. So here's the summary. There was between 21 and 35% carbon, so very rich in organic matter. We had 50 to 221 grams per kilogram iron, so fairly rich in iron. I will show what this iron is in a minute. And we had up to 2,600 ppm or milligrams per kilogram of arsenic in these flocks, so they're very rich in arsenic. This is how these flocks look like on an optical microscope, and these are DAPI-stained images showing that there are some cells. You can see some algae in there. You can see iron minerals, and it's a quite heterogeneous mix of materials. If we look at the arsenic EXAF spectra, this time we only needed 2 reference spectra to describe the unknown samples. These are shown on the top, arsenic-3 and arsenic-5 sorbed ferrihydride. These are 6 different flock samples. You can see they all look more or less the same, and they can all be very well explained by these 2 references. And the summary of this is that arsenic is mainly adsorbed to iron oxide minerals, and it's 70 to 84% arsenic-5, and 16 to 29% arsenic-3. And this is not really surprising because these surface waters are pretty much oxic most of the time. So you would expect that arsenic-5 is the more dominant species in these flocks. If we look at iron EXAFs of these flocks, again, you can see these are many different flock samples. You can see the spectra look all alike, so meaning that the iron speciation in the flocks is also very similar between the flocks. There's not so much variation. And all these spectra can again be explained by 2 references, and that is a ferrihydride, a very poorly crystalline iron-3 hydroxide, and lepidocroside, the top spectrum. And if we do the linear combination fitting, in summary, there was 50 to 70% of the iron bound in ferrihydride and 30 to 50% in lepidocroside. Now, interestingly, the lipidochroside was not detectable with X-ray diffraction. And so we wanted to have another confirmation for that, and we were able to do some Mössbauer spectra together with Andreas Kappler's group in Tübingen. And these are some Mössbauer spectra at room temperature and 5K. And I just want to summarize the result here and compare it with the EXAFS data. And so this shows the ferrihydride and lipidochroside mass fractions determined by EXAFS. And this is by Mössbauer spectroscopy, and they agree very well with each other. So I think this was actually a good confirmation that indeed it's lipidochroside. And what this means actually is that this lipidochroside in these samples is extremely nanocrystalline. It's so nanocrystalline that it cannot be detected by X-ray diffraction. It's very nanocrystalline lipidochroside, but it's clearly different than ferrihydride. And you will see later that it has a different reactivity. So now we know what is in these flocks, and now we did an experiment to look at what happens if these flocks are exposed first to iron 2 and then to sulfide. So the experiment is fairly simple. We take a flock suspension, put it in these septum bottles, spike it with iron 2, and then follow the speciation changes over time, and also follow the arsenic release. So in order to explain a little bit more the concept of this experiment and what might happen, I made a little cartoon here. So this could be the flock sample with ferrihydride and lipidochroside. We spike iron 2, but in this experiment we used an isotopically enriched iron 57 spike. So this contains 95% iron 57, and the natural abundance of iron 57 is only 2.12%. So natural abundance iron has this isotope composition. So the flocks contain 91.7% iron 56 and only 2.1% iron 57. And we spike the iron 57 here for two reasons. One is that we are able to follow the kinetics of atom exchange between the spiked iron and the flock iron. And the second is that iron 57 is Mössbauer active, so we can also follow where it goes or what type of mineral it forms. Okay, so what could happen is that this iron could get absorbed to the flock material. This will be a pH-dependent process, of course. So at high pH, we have more sorption. At low pH, we have less sorption. And the iron could then get oxidized by releasing an electron, for example, into lipidochroside or ferrihydride. And this electron could reduce another iron atom somewhere else. And this will most likely be in iron 56 because there's a initially 91% chance that this is iron 56. This can get released into solution, and so this can drive a recrystallization of the solid phases. This is well known for ferrihydride. And so what we should then observe is a change in the isotopic ratio here, so we can monitor the isotopic ratio in solution to get some handle on the kinetics of this process. And in principle, if the system, if everything exchanges, the system will reach an isotopic equilibrium. And so if you plot the isotopic ratio in solution over the ratio in the entire system, we should reach a value of 1. But if there's a fraction that is not exchanging at all, that is inert, it will level off at a lower level. Then during this process, we might have mineral transformations, maybe forming more crystalline iron phases, and there could be a release of arsenic if there's recrystallization and a loss of arsenic sorption sites. So let's see what happens. So the way the experiment was done is we took these septum bottles with 2 grams per liter of flock material. We also did the experiments with pure ferrihydride and also with a ferrihydride polygalacturonic acid coprecipitate. That's kind of a synthetic iron organic coprecipitate. Then we spiked iron 52 with 2 different iron 2 concentrations. These are the final concentrations in the system. Incubated these samples for 7 days in an anoxic glove box. We then took some aliquots after different time intervals, prepared them for analyses, and used different techniques to analyze the solution in the solid phases. So first I would like to show you the iron speciation, and let's first focus on this here, the pure ferrihydride, so synthetic material. This is the initial ferrihydride spectrum, 100% ferrihydride, and if we spike this with iron 2 at pH 7 at 0.1 and 1 millimolar concentrations, we see that we form goethite. This is goethite, this is lepidochloride, and at the higher concentration, we completely transform this ferrihydride to goethite and lepidochloride. So it's completely transformed. We do the same with the ferrihydride coprecipitate, polygalacturonic acid. There's no change. We still have the ferrihydride at the end. And in the flock samples, this is shown down here. You can look at the linear combination fitting results. Of course, we have ferrihydride and lepidochloride present initially, but there's not so much change. Maybe in the highest spiked iron concentration, pH 7, there could be some goethite formation and maybe some lepidochloride formation, but it's much less than for the pure ferrihydride. So this tells us that, or it suggests that the natural organic matter actually inhibits a recrystallization of the polycrystalline iron phases, but it doesn't tell us anything about possible atom exchange. It could still exchange, but you might form new ferrihydride in the presence of organic matter. So it's important to also look at the isotopes, and if we do that, we find the following results. The top curves, this is now R over R system, and the top two curves are for pure ferrihydride at pH 7 at 0.1 and 1 millimolar spiked iron 2. And you can see that they both very rapidly approach a value of 1. So there's a lot of atom exchange going on in the system. If we reduce the pH from 7 to pH 5.5, this is the pure ferrihydride at pH 5.5, it's much slower. And this is because there's a lot less sorption of iron 2, and therefore it's a much slower process. If we do the same experiment with the ferrihydride polygalacturonic acid at pH 7, we see a rapid reaction initially, but then it's completely leveling off. So it seems like it really stops reacting. So there might be some part of the iron protected. And with the flocks, we also see a rapid initial reaction and then a very slow reaction, but it's never as fast as with pure ferrihydride. So again, also here, it seems like the organic matter has a big influence on not only the recrystallization, but also on this atom exchange process. We don't really understand fully why this is the case. These data are, of course, only the solution side, but you can use them to calculate the percent atom exchange. I just want to show this briefly, that in the pure ferrihydride, we indeed reached 80 up to 90% atom exchange, and in the flock samples, maybe 20, maximum 30% atom exchange. Arsenic release was not detected in this experiment. And this is actually now not so surprising because there was no recrystallization, and so the material retained its absorption capacity. So the gray area, these are controls, and these are the data points, and there's no significant release of arsenic. What about the sulfide experiment? So in the second experiment, it's the same idea. We took basically these blocks. This time we spiked sulfide and followed the speciation changes. So here, this system is significantly more complicated chemically, I think. And so what could happen is it's quite well known that actually sulfide can react with iron minerals to be oxidized to elemental sulfur, and the iron gets reduced to iron 2. This elemental sulfur can further react with additional sulfide to form polysulfides in solution. And the iron 2 could now drive mineral transformations, similar as I showed before. Or it could also get precipitated with sulfide if there is enough sulfide to form makinavite or some polycrystalline iron sulfide precipitate. The sulfide could also react with natural organic matter to form new thiol groups, and those would be very efficient sorbents for arsenic-3. And finally, there could be arsenic release from the flocks, and the arsenic could react with the sulfide to form diolated arsenic species in solution. And this could be relevant because these diolated arsenic species are known to absorb much more weakly than inorganic arsenic species, or than arsenate and arsenite. So it's a quite complex system, and if we want to understand this, we really need to look at arsenic, iron, and sulfur speciation, both in the solution phase and in the solid phase. So let's see what happened here. So we did a similar experiment. This time we used 1 gram per liter solid concentration. We had 4 different flocks for this experiment. It was all done at pH 7. We spiked sulfide at 2.5 millimolar. It's actually a fairly high concentration, I must admit. We incubated the samples for 7 days, again, took aliquots after different time intervals, prepared them, and used various techniques to analyze the solution and solid phases. So I want to first show you what happened with the sulfur. So this shows on the left side elemental sulfur, and this is for these 4 different flock samples, and always showing 0, 0.3, 3, and 7-day incubation. And you can see that for all 4 different flocks, we have a very rapid increase in elemental sulfur. What you can also see is this is for unfiltered and for filtered samples. Unfiltered means this is the entire suspension. So it means basically the dark blue bars are elemental sulfur associated with solid phases, and the light blue bars are dissolved elemental sulfur. So it means that most of the elemental sulfur formed was associated with the particles. On the right side, you see polysulfide formation. And again, oops, sorry, I'm pressing the wrong button here. Again, you see that there's a very rapid formation of polysulfides, mainly S5 and X6 are the biggest fractions. And also these polysulfides turn out to be to a large degree associated with the particle surfaces. So this is simply the result of this reaction that I showed, that part of the sulfide reacts with the iron minerals to form elemental sulfur and polysulfides. This really happens. It shows that the flock iron is very reactive, actually, with respect to sulfide. It's not protected by organic matter. We also looked at sulfur speciation using sulfur xanes at the synchrotron. This shows a sulfur xane spectrum for an untreated flock samples before the spike. And you can see this is reduced sulfur, this is some oxidized sulfur groups, and you can further deconvolute the spectra. And in the reduced part here, you see probably some exocyclic or elemental sulfur and some heterocyclic organic sulfur, but only very little inorganic sulfide. And then you have different oxidized sulfur species. After spiking and incubating for 7 days, we have a very different spectrum. And we have 2 peaks that are strongly enhanced. And one is this peak for elemental sulfur, which could also be exocyclic organic sulfur, but it's very likely that elemental sulfur is here a big contributor. And then also this second peak for inorganic sulfide, which was very small here, is now very strong. And this indicates that there might have been precipitation of McKinnavite as an inorganic sulfide mineral. Now, if we look at the iron speciation, on the left side, we see dissolved iron 2 in solution. And you can see that in all 4 flock samples, we saw a very strong increase and rapid increase in dissolved iron 2 in solution. The control had no release of iron, but the degree varied between the different flock samples. We look at the solid phase iron speciation. These are the initial speciation results. Again, some lepidochrosite, and the white bars are ferrihydrite for the 4 different flock samples. And if they are spiked with sulfide and incubated for 0.3 and 7 days, we see a completely different iron speciation. And we see mainly formation of macinavite at the expense of ferrihydride. So in the top two flock samples, we didn't detect any ferrihydride with XAFs anymore, and only macinavite and lepidocrosite. So it seems like the ferrihydride was completely transformed to macinavite. And in the lower two samples, this conversion was not complete. There was still some ferrihydride left. So the explanation for this is probably the different ratio between spiked sulfide and total iron in the system. And the reason for this is that, remember, we used a constant solid to liquid ratio, but the flock samples had different iron contents. So the iron content in the flock sample is not constant, so therefore this ratio was not constant. And in the top two samples, we had ratios above 1. So we had the highest ratio here and the lowest ratio here. So we think that this is probably the reason why the transformation was not complete in these cases, because it's just less sulfide compared to total iron. If we look at arsenic, we also see a fast increase in dissolved arsenic in solution in all 4 flock samples. But in 3 samples, it decreased again. In the control, there was no arsenic release. And we had 1 sample where it continued to increase. We'll come back to this in a second. If we look at the solid phase speciation, again, initially we had mainly arsenic 5 and some arsenic 3 adsorbed to ferrihydride or to some iron oxyhydroxides. And after the spike and incubation, we saw that the arsenic speciation in the flocks also changed. We saw some formation of arsenic 3 adsorbed to macinavite. And in this sample, which was the highest sulfide to iron ratio, we also saw some arsenic sulfide mineral precipitating, that's orpiment. And again, these differences might be due to the different ratio between spiked sulfide and iron. Now, let's look at this particular sample here more closely, and I would like to show you also the arsenic speciation in solution. This was the sample with the highest excess of sulfide. And here we found that in solution, a very significant fraction of the arsenic, the dissolved arsenic, was present as thioarsenate species. This is monothioarsenate, dithioarsenate, and trithioarsenate. And these species are known to form in sulfur-rich systems, for example, hydrothermal systems or other sulfur-rich environments. And this can be quite important because these thioarsenate species are known to adsorb a lot less to oxide minerals than inorganic arsenic or arsenate and arsenite. And so this might help in part to explain the higher solubility of the arsenic here, but maybe it has also to do with the macinavite that formed in the other samples. So in conclusion, in these experiments, we found that the natural organic matter actually hindered iron-2-induced atom exchange and recrystallization of these iron oxides, which is a very well-known process for pure iron minerals like pure ferrihydride. But in these flock samples, it doesn't seem to occur. And as a result of that, exposure of the flocks to iron-2 did not result in arsenic release. Maybe it would if we would go much higher in concentration, but we kind of wanted to stay at environmentally realistic concentrations. But we showed in the second experiment that flocks are very reactive with respect to sulfide. And so if we spike sulfide, we rapidly form elemental sulfur, polysulfides, iron-2. There's enough sulfur, we will precipitate macinavite and even orpiment, and also find some thioarsenate species in solution. And the result of this is a rapid release of dissolved arsenic. So it shows that if there are sulfur-reducing conditions and sulfide produced, that this could be very reactive and result in the release of arsenic. Of course, it always depends on elemental ratios, and admittedly, we used a fairly high concentration of sulfide here, and it always depends on whether there's enough sulfide available. But with this, I hope that I showed you a little bit what might happen with arsenic in such a peat environment, and I would like to acknowledge not only some of my group members who helped, my collaborators, also the beamline scientists at different synchrotron beamlines, and our funding, which mainly came from the Swiss National Science Foundation. And if you're interested in our work, I would like to invite you to visit our group's website. And you can find, for example, all PhD theses are all online. You can freely download them. You will find our publication list. And so if you're interested in reading up on some of this work or other work. And so this is a fairly recent picture of my group. We like to go to the Alps for hiking. And this seems to be winter in Zurich. Not as nice as right here. And right now the group is not so large, but since 1999, I've graduated 25 PhD students. So you will find a lot of different topics if you look at these PhD theses. With that, I'm happy to take any questions. Thank you very much.
Any questions?
Yeah.
Thank you, Ruben. I have a question. If I understood correctly, on the one hand, you decided something was dissolved because it went through a 0.2 micrometer filter. And on the other hand, you said there were nanocrystalline items in the systems. Is it possible you have sub 200 nanometer things moving around?
I mean, these flock samples, these flocks are fairly well aggregated and fairly stable. So I'm not saying it's impossible that something would even pass a 0.2 or even smaller filter. I mean, we did some experiments with even smaller filter sizes, and at that cutoff, we didn't find any effect. So we assume that this is really soluble or dissolved.
So let me turn the question backwards then. Do you have thermodynamic data to solve for the precipitation of these things given known solution conditions? Including the Kelvin effect, of course, for the size of the particle. I'm trying to support the theory that
okay. So you were asking whether the solutions might have been supersaturated with respect to some mineral phases.
Yeah.
I mean, the iron that goes in solution is all iron 2. And so and iron 2 is quite soluble. I mean, it's not supersaturated with respect to any mineral phases. Like iron, McKenna-White could possibly, we didn't calculate that. But the problem was that we didn't follow the inorganic sulfide concentration in solution. So we can actually not make this calculation. We would have to also measure inorganic sulfide, but it's a good idea.
So you mentioned that you saw some pyrite dissolution when you were working with the peat sediments. Did you see the associated pH changes that you normally see, say when you have acid mine drainage, where the pH drops rapidly?
Yeah, I mean, I showed you at the beginning. I showed one graph where you saw that pH decreased and pH increased, and of course, I mean, the amounts of pyrite that are there are not huge. But it's still, it's a fraction of the total iron, and for sure it contributed to this pH decrease. But it might not be the only factor that contributes to the pH drop.
Couple questions. So one is, in your peat study, in the superficial layer, you have iron oxyhydroxide, and also realgar, I think it was. So how are those coexisting? That's one. And then, the other is, for the flocks that are complex with organic matter, the iron 2 isn't reacting. Do you think they're less biologically reducible as well, for dissimilatory metal-inducing bacteria?
Okay, so the first question was about the surface peat layers, and you're right that the speciation is quite mixed, and it's not in some kind of thermodynamic equilibrium. And the only speculation about that I have is that these surface layers might have variable redox conditions. So you might have phases where you have strongly reducing conditions, and then you have phases where it's more oxidizing. And if the oxidation and reduction reactions are not very fast, then you might have, a mixed speciation at a given point of time. But it's a good question, and it was a little bit surprising to us too that we found arsenic sulfide minerals in the top layers and not in the deep peat layers. We had expected them more in the deeper peat layers, actually. The second question was about the
reducibility of the flux.
Oh yeah,
complex.
Yeah. I mean, that's a very interesting question that we haven't looked at yet, but I think it would be a very nice experiment to see how reactive or how bioavailable the iron in these flock samples is for microbial reduction.
People have done tons of work on ferrihydrite, but is it representative, the pure ferrihydrite of environmental phases?
I mean, we don't really understand yet why the NOM prevents the iron atom exchange and the recrystallization. I mean, the recrystallization, I can imagine it may poise crystal growth and so on, but there could still be atom exchange and under formation of new polycrystalline phases. And one possibility that we have to look at more carefully is whether some of the iron actually gets absorbed by organic matter and maybe just oxidized by organic materials in there. Because we know from some other studies that, for example, the PGA coprecipitate, it was very reactive for ligand-controlled dissolution. We published a paper some years ago where we looked at ligand-controlled dissolution of ferrihydrite polygalacturonic acid coprecipitates. And it is reactive, and also the sulfide experiments show that actually the surfaces are not blocked. I mean, it's fairly reactive material. So we don't fully understand why the iron 2 doesn't react so rapidly. So maybe the organic matter is catching some of the iron, and we need to look at that more carefully. It's a little hard to pick up because of the iron ratios that we use.
First one is, this is not my area at all, so very nice question. At some point you mentioned that certain species could not be measured with X-ray, but then you measured in other ways. So in general, is this just a matter of size or of the granularity of whatever material you're trying to measure, or is there something else there that makes one species not measurable in X-ray but measurable in other methods?
What context do I? Mm-hmm. Oh yeah, okay, I see what you mean. So that particular example was, so when we did bulk EXAFs, we take bulk peat samples, homogenize them, take them to the synchrotron, we do the spectroscopy, and typically, one says that, you can pick up a species if it's maybe present at least 5% or so of the sample. If it's lower than that, you will not be able to detect it because it's just covered up by oscillations of other species, and it'd be very unreliable. And
it's a concentration, not
it's
not
a
a particular
it's like the detection limit
size.
of bulk EXAFs for a particular species is typically maybe not lower than 5%. So if we go to a microscopic technique where we are able to do locally resolved spectroscopy, we could find even something that is present only in 1% or lower if we happen to find a grain where this species is present and where we can collect a spectrum that actually proves that that species is present. It's just a matter of detection limits of the technique.
Average for the full sample.
Yeah.
And my other question was sort of more broadly with this, with the second experiment showing that you have arsenic basically production. Is this now telling you something about where you're more likely to have arsenic as a hazard in certain areas, or I mean, what's the next step using this for sort of inferring risks for public health?
Yeah, I mean, here our main goal here was to understand how the speciation is in this peat system and how it could change if the redox conditions could change. But you could imagine that, let's say, if such a peat system would fall dry because of changing hydrology. So in the Alps, we have a lot of glaciers that are disappearing, a lot of rivers fall dry during the summer. So it could well be that some small wetlands fall dry and then get oxidized, and there could be, potentially there could be some leaching of arsenic out of such system if it gets oxidized and then mobilized. I mean, this is just one idea that...
so when they would dry, then that would mean that's the best mimic for your silicate experiment? Or
then basically the peat would get oxidized. Arsenic could get oxidized from arsenic 3 to arsenic 5. It could become more soluble and then be leached out with the next, waters coming back in it. There could be some arsenic release. But this is a very hypothetical case. I mean, this particular wetland is at the moment not in danger of falling dry. It was more like a very nice natural system where we had a natural enrichment of trace elements over a long time period. So for us, it was like a nice system to study the speciation and the fate of such elements in such an organic rich environment. I think it's more that than the environmental relevance of this particular wetland.
I was wondering what caused the enrichment of arsenic in other like trace metals in this peatland. Is it just groundwater discharging and then accumulating over time, and is it normal concentrations in the groundwater, or do you see extraordinarily high in the groundwater?
Yeah, it's I showed in one slide. There's a little like an inflowing stream which contains it was reported to contain 450 micrograms per liter of arsenic, so it's higher than normal groundwater would be. And over long time periods, if the arsenic is trapped in the peatland, then you can get natural enrichments in the peat. And the same is true for selenium and arsenic, but I don't know the dissolved concentrations in this inflow, but I think they come through this little stream and these are trace elements that stem from rock weathering. But I cannot tell you the exact source of that.
To see, like in a lot of peatlands that have, say, just a groundwater fed but don't have particularly contaminated groundwater, would you expect to see really high enrichment of arsenic then? Like, is this something that you think is more widespread?
Yeah, I mean, there are many peatlands, of course, that are not as enriched in trace elements as this one. I mean, in fact, I mean, the Alps, in the Alps we have a lot of little small peatlands, and there are very few data on trace metal concentrations of these peats. I mean, some have been used like to study atmospheric deposition of trace elements, like an archive, but there are not many data about like naturally enriched through geological weathering enriched peats. I suspect there are more, and I mean there are some other areas where people have done similar studies, but I cannot tell you how widespread it really is in the Alps, for example. There are just no data. I don't think that. I think it's special situations. But for example, it is quite well known, meanwhile, established that in Southeast Asia, in the sediments, that you find old buried peat layers. And there are many papers, meanwhile, that show that these peat layers are also quite enriched in arsenic. They often contain much more arsenic than the mineral aquifers below and above. So also there, it seems like that these peats acted as biogeochemical traps for arsenic, which was enriched during the, probably hundreds or thousands of years of peat formation. I mean, the peats in the Alps are typically not older than 10,000 years, say. I mean, they were all formed after the last glaciation. And, but this is the time period where you can have accumulation of trace elements. And if you have like a stream coming in that constantly brings some trace elements, and if they're trapped, they will be enriched in this. Okay, thank you very much.